Talk about it. Each Friday at this time, hosts Dennis O'Brien and Susan Johnson interview guests who are involved in their community. The show challenges conventional thoughts, probes for answers, remembers the past, imagines the future, and gets to the heart of the matter. Let's Talk About It is brought to you by Columbia Ford Kia, Route 6 in Columbia, Connecticut, and Gates GMC Nissan, Route 66, the Boston Post Road, North Windham, USA. Opinions expressed do not necessarily reflect those of WILI staff, management, or sponsors. Now, let's join our hosts with their guests, and let's talk about it.
Hey, good evening, everyone, and welcome to another edition of Let's Talk About It. This is Susan Johnson, and my co-host, Dennis O'Brien, is out doing great things in the community today. But I do have a co-host, our town manager, Rob Zarnetske. Welcome to the show, Rob.
Always a pleasure.
Great to have you here. And we have a wonderful guest, don't we?
We do. This is one of the more interesting guests I think we've had on WILI in a while, out of state and dealing with some really interesting technological changes that are happening around the world.
I'm very thrilled to have Paul Kohl. He's a professor of engineering at Drexel University, and he's going to talk to us about all things geothermal. And this is something that, as you know, I've been very, very thrilled about, because what I've been able to do at the Capitol is create in Senate Bill 4, a big section that addresses geothermal heating possibilities in the state of Connecticut. And we also have bonding set aside for $25 million. So I'm hoping to get this show over to the governor as well and make sure he knows, in our Department of Energy and Environmental Protection, so that they hear it. And of course, our university here, Eastern Connecticut State University, is all about sustainability and does have geothermal, as well as our generations. Federally Qualified Health Center, they have geothermal, because what? We sit here on an aquifer, otherwise known as a lake, right here on Willimantic, and I chair inland wetlands and water courses. So I'm all about using all the things that we have.
It's exciting, and I'm going to point out one other connection here that I think is important. Connecticut has been a leader in geothermal and is taking the lead in sewer thermal, which is a sort of subset of geothermal in a lot of ways. Dr. Kohl is actually the chair of an organization that was established here in Connecticut. He's the head of a nonprofit organization that's headquartered here in Connecticut that is focused on making sure that the world understands that you can draw the energy out of the water that you've let go down your drain. There's a lot of energy in the water that we dump down the drain after showers and after washing our clothing and all of that. His nonprofit organization is all about making sure that people understand how you can extract the heat back out. He's also the head of a company that he runs. So he's got the nonprofit, and he also has a company called Kohl Energy Recycling that actually focuses on private sector projects to get energy out of the water that's been otherwise, the heat that's in the water that otherwise would be wasted.
Well, we've got to recycle what we've already used. If we have energy we've used and we can still use it again, we should use it again. Makes everything much more sustainable. Understanding that is why we're so thrilled that Professor Kohl is here with us. Well, welcome to the show, Professor.
I'm excited to meet this person. He sounds wonderful.
I think you might know each other.
Well, thank you for having me on. And Robert is a dear friend and colleague, and I appreciate being on the show with him. So it's nice to meet you, Representative Susan Johnson. It's very nice to meet you.
Well, thank you. It's great to have you here, because this has been one of my hopes for our state, for our town, and for the country, really, because I think that we are missing out on reusing our energy, and we don't want any energy to go to waste. We need to understand how things work, and that's one of the things I'm just so pleased that you're here to help us out with that information.
I'm very excited to talk. Also, laying some ground rules. You should cut me off at any time, because Robert and I work it. I can start talking, and you should just say something, and I'll stop, because I tend to rattle on.
You haven't noticed I do that too?
You are both passionate about this subject. There's no doubt that you both care about this.
All right.
So even when you keep saying geothermal, and sewage thermal is a form of geothermal because it is in the ground. And in fact, that's when I first was introduced to it. It's like in 2010. It was a sort of concept. It was just geothermal, and the similarities, geothermal and sewage thermal. Again, Earth. They're both underground. They both are water based, and that's sort of like a big presumptive start. When you try to use a heat pump, and a heat pump is a thermodynamic cycle where you have a compressor and a condenser and a boiler, and you also have or an evaporator, and you have a pressure reducing valve. You learn this in your first year of engineering or science when you learn thermodynamics. Actually, I think now high school students are learning this. So I'm just learning my age. But a heat pump is basically an air conditioner. An air conditioner is a form of a heat pump, so you can either run it forwards or backwards. So it's either blowing heat into your house or blowing cold into your house. That's a heat pump. And we're used to air-sourced heat pumps. That's what you go outside and you see this big unit. It's got a fan and it's humming, and you're like, okay, that's where my air conditioning is coming from. A water-based heat pump doesn't make that hum noise, and instead of passing air over the coils, it passes water over the coils. And we have found out, and we've done studies. In fact, ASHRAE, which is an organization for heating and cooling, did some experimentation. And if you use a water-to-water heat pump, you use half the electricity to produce the same heating and cooling as with an air-sourced heat pump. And the main reason is, and it's funny, I'm so used to having a chalkboard or a whiteboard or something. The reason is that water is much better conducting heat, transferring heat than air, and it's much denser than air. So it is literally 4,000 times better than air.
Wow.
So geothermal and sewage thermal are the best forms of heat pump sources because it's a water-to-water thing. So right from the get-go, they blow everyone out of the water. Everyone's less than they are.
That's wonderful. I have a question about that because I would like to know if you could give me some timelines for how long the heat pumps that are water-based work.
May I ask you to ask the question? I don't understand the question.
So I guess the thing to know is how long is a pump good for? If you're gonna install one of these in a commercial building or in a residential building, how long would it last?
Oh, you know what? All these things are sort of dependent on the quality, the maintenance, and also the quality of the material. But it's like an air conditioning unit. It'll last for 20 years. It'll last for 30 years. If you beat it up, it lasts for 8.
Right.
But it's a standard. HVAC is heating, ventilation, and air conditioning. So HVAC, it's a standard HVAC piece of equipment. A water-based heat pump will last just as long as an air-based heat pump, if not longer. People with geothermal systems, in their houses, you could ask them. These things are long-lasting. They're more reliable than your standard water heater, and probably than a low-end, forced air heater. But they are mechanical in nature. They need some maintenance, but they're pretty low maintenance, pretty low. They're very simple devices.
This is a great point for me to ask another question for people that don't understand a lot of this, and that is, what are the things that you might have to replace on a regular basis with a water-based heat pump? Well, it's the best illustration is an air conditioner. Mm-hmm. So in your house, if you have a central air, you turn it on in the summer, you turn it off for the winter. A heat pump is you turn it on for the summer and you leave it on for the winter. You just switch the sides. And so, like anything else, if you have a thermodynamic loop which has a refrigerant in it, it is the refrigerant that does the transferring of heat from one sink to the other. And I say sink, so let me stop using engineering terms. So the reason we call it a heat pump is a heat pump can take heat out of water at a lower temperature and rise it up to a higher temperature. And just like a water pump that pumps water up a hill, a heat pumps heat against grade. Temperature always wants to decrease. So like if you've got a hot object connected to a cold object, the heat flows from hot to cold. That's natural. That's like water flowing down a hill by gravity. A heat pump reverses that. And that reverse takes energy, which is what drives the system. And the mechanism that we use, or the fluid we use, is called a refrigerant. So
even when it's, so either heating or cooling, we still call it a refrigerant. And we used to use Freon. We no longer use Freon. But, something like that is a refrigerant. Now, what I'm saying that is that if you have an old system, you've got your Freon, you've got your refrigerant loop. Sometimes you lose some pressure. You've got to call an HVAC person. They've got to repressurize your system. They've got to add more coolant. Things like that are maintenance. It is a compressor. A compressor takes a vapor and pressurizes it, increases its pressure greatly. And because of the relationship, again, you learn in high school physics, is PV equals nRT, which is pressure times volume equals N, as a coefficient number, times the Rensselaer coefficient times temperature. So PV equals nRT. What we know is that if you drastically increase the pressure and you drastically reduce the volume, and increase the temperature.
So
that's how we get temperature changes.
For folks out there listening to this, I guess one of the questions that comes to mind is, if you've got to put electricity into the system, if you've got to run the heat pump using electricity, how do you save money? Why do this? I mean, what's the benefit to running a heat pump, whether it's air cooled or air heating or water based?
That's a great question. It's ultimately the most efficient heating system in the world is a heat pump. Its efficiency, because of the way the cycle works, theoretically is greater than 100%. But since you can't really be 100%, we don't use percentages with heat pumps. So what we say is, if I want to move 300 joules of heat into a building, and I have a water supply, I can put 100 joules of energy in there. I'll take 200 joules of energy out of my source, and I'll produce 300 joules of energy into that house. That's a coefficient of 3, a coefficient of performance of 3. So I can take the amount of energy, work, that I'm putting in electricity, and I can multiply it by 3, 4, sometimes up to 5 times. So it is an extremely efficient form of heating and cooling. And back to the recycling element, if the source of that is a relatively warm product, it makes it much easier for the pump to lift, and you get a lot more
and
heat for less
and
food.
that's where geothermal and sewer thermal come in, because you've already
Very
got water
similar
at a warmer temperature than you'd have at the surface. If you drill down into the ground, you've got water that, if I'm remembering, it's about 50 some odd degrees Fahrenheit.
Yep, a bit. Yep.
And if
55, yes.
And if you're looking at sewer thermal, if you're looking at wastewater coming off of industry and coming out of residential buildings, you're looking at something closer to 70, is it?
Yeah, 65 to 70. It's it depends on your averages. In the middle of winter, it's almost down to 55. In the middle of summer, it goes up. But generally speaking, in fact, I've done some research on this, as you would imagine. The average is 68, at least here in Philadelphia. So 65 degrees is a good number. So it's a better temperature source. It's warmer, so it's better at removing heat in the summer. The thing that really makes it superior to, if you have access to sewage thermal, it's almost always more efficient than geothermal, because geothermal relies on an interface of a vertical well that goes down. And there's different ways to do a vertical well, but for the most part, you take a pipe, you put it in the ground, and inside that pipe you put a loop, and that loop is like a plastic tube, fairly dense plastic tube. You pump water in on one side, it goes all the way down to the bottom and comes back out the top. And while it's in there, it absorbs heat from the surrounding environment. It has a kind of a thermal capacity based on the flux, which is energy moving through an area. The flux of heat, which gets connected to that well, it's called a borehole. Now, in sewage, the sewage is flowing, so the sewer is always, even if the sewer was exactly the same temperature as a bore field, it replenishes every second that it flows. Therefore, it's got multiples of capacity. It's got much more capacity than a well field. The two work good in tandem, or using them in conjunction. But if you have access to a flowing sewer, it has a tremendously large amount of thermal capacity.
And so the benefit here, then, it sounds like, is because you can heat the water that you're using to drive the heat pump using the groundwater or the sewer water, because you've got this warmer source of water, you don't have to use energy to get that temperature up. It's already high to begin with, and then you're just lifting it a little higher.
Yes, that improves its performance.
Yeah.
But you still need energy. You need to run the thermodynamic machine, which is the heat pump.
Right.
So
and so
it always takes...
That brings us back to the question, I suppose, how much do we save?
Oh, that really is on a case-by-case basis.
Yeah.
And it's... you know what? It's very difficult. You know, I'm going to start talking circularly, so I'm going to have to prevent myself.
No, I guess we could, for our purposes here, just, people are building geothermal systems and people are building sewer thermal systems around the world. They're doing it because it's economically beneficial. They're not just doing it because it's theoretically efficient. They're doing it because those efficiencies drive savings.
That is correct, and the amount of savings depends on the differential between the cost of electricity versus the cost of a fossil fuel. And currently, in the United States, we don't have a carbon tax, so the amount of carbon you liberate through your heating of your home is free, when it does have a social cost to the world at large.
That's a good point.
The other question I have is that there are places, and I'll go to the extreme, like Iceland, that's all geothermal and quite easily able to extract the warmth from the existing area because of the volcano and all of that. And so they are able to heat Iceland with geothermal. And it's all geothermal, which saves money, and they're very sustainable, and they aren't reliant to any great degree on fossil fuels. As we transfer, as long as I got that concept down okay, I'll move over here to urban areas here in the United States. Urban areas in the United States almost invariably have sewage treatment facilities. Sewage treatment facilities. Now, tell us a little bit about how you would use sewer thermal, because a lot of people don't understand that it's a separate pipe for the geothermal or sewer thermal.
This is where I get to. I do want to go into more depth about true geothermal. Mm-hmm. In Iceland, they do what is known as true geothermal. They go far enough down that they're actually tapping energy from the core of the earth. The center of the earth is a ball of molten minerals, metals. So they're far enough down, and they're close enough to where the magma is close enough so they're using true geothermal. Now, we call geothermal when we draw a well 300 feet down to the ground, but ironically, that's solar energy. That's actually energy from the sun. So all the geothermal that you and I are talking about is actually solar energy.
That's interesting, because the surface at 300 feet is still just radiated heat from the top.
Radiant heat from the sun, yes.
Yeah, interesting.
Only when you go to Iceland and or these other places that have these really deep wells that actually do touch the core, that actually get on the periphery of the heat of the core, those are truly geothermal. And not only do they produce heat, they have enough heat that they produce steam, which makes electricity. You're right, Iceland is just sitting on a very sustainable energy source, and all they had to do is drill a hole to get it. So I don't really want to spend too much time on that, but I do. I just felt as if I should talk about that. But
it's a fascinating.
Perfect. No, I think it's a great way to kind of transition people into thinking about how do we deal with the fact that we're creating energy when we get our water from a lot of people have here in Willimantic, for example, we have the Willimantic Water Works. So we have a waterworks system that comes in through pipes into our homes, but we also have sewer system that goes out of the house and into the sewage treatment facility. But in terms of one of the things that we take a look at, and I'm just learning about this. So my understanding is you'd have to dig a hole, say where your sewage pipe is, and put a geothermal pipe near it or under it, and then utilize the energy from the sewage pipe by piping the geothermal fluids that are going to get the recycled energy from the sewer pipe.
Yes. There's two main techniques that we're going to talk about, to think about. One is you can actually interface with the sewer. You need to interface with the sewage fluid. Another very seminal piece of information is sewage is 99.5, 99.8, 99.9% water. It's really water. This is also interesting to come back,
which means it's not solids. We tend to think of it as
right.
Solids.
Right. So this is also for food waste co-digestion, which is another topic. But we as humans are like 65 to 70% water. So we're ourselves kind of big sacks of water. Our food is a big sack of water. When we go to the bathroom, it's just the same big sack of water. So it turns out that wastewater in a sewer is really all it's contaminated with sanitary waste, but it is really water. So you've got flowing water. And the reason I say that is that now you have to interface with that water. So generally speaking, we use the material called stainless steel because stainless steel doesn't corrode and it transfers heat greatly. So it's a wonderful metal to use. Another good metal to use probably would be gold, of course, right, as if we would put gold in our sewers. But the point being is that you'd want a non-reactive metal that conduct heat. So you can put them directly in the sewers, and then you connect those to things, or you can have a hole that pulls sewage out, and then you have the heat exchanger outside of the sewer, and you pump the sewage back in. Those are the two main ways you do it, but you have to interface directly with the sewage water. Now, that being said, that's the what we call the dirty side, or the actual connection side. That's a thermodynamic loop, and then your heat pump would connect to that loop, pulling energy out or putting energy in. But that's where you would do it. The thing you just described could also be done, which is you could make a well field near a sewer, and you would get some of that heat. But that would be less efficient, and you'd sort of be insulating yourself against the actual thermal transfer that you're wanting. But it's a possibility. You could do something like that, which would be an interesting thing. But I'm sorry, now I'm just talking about possibilities. The reality of it is that the devices that are made are either stuck into the sewer or the sewer water is extracted and then returned.
But the coolant or the refrigerant, the water that is flowing through or to the heat pump, though, is isolated from the
absolutely.
Yeah.
It's an absolute separate loop.
Yes, and that's, I think, something that we're going to try and clarify a little bit more as we go through the discussion. But right now, we have to take a break and have our sponsors take care of us. And we thank Denny Gates and Gates GMC for being our sponsors. And we will be right back after these messages. Welcome back, everyone. This is Susan Johnson. I'm here with our town manager, Rob Zarnetske, and our very, very special guest, Professor Kohl, and he is here to talk to us about all things geothermal, including sewer thermal. And he's going to go and explain a little bit more about how sewer thermal, we're just taking the energy, but we're not taking anything else. It continues to go through the treatment process that we normally use to clean all the things that come from our homes and into the sewage treatment facilities. So please proceed, Professor.
Yes, well, I appreciate the prompting, and that's 100% true. There does need to be an interface between the sewage itself, because that's where the energy is, and your system. But that's done through stainless steel heat exchangers and a closed loop. We call it a closed loop because nothing goes in and out of it. It just circulates in a pattern. So that closed loop is a water with a little bit of something called propylene glycol in it, or just a little bit of a anti-freezing device or material. I'm getting. You don't need to know all that. The point being is it's a closed loop, so the people that are using the heat or the cooling are not having interface with the sewage. That heat is pulled off and put into a loop, and then that loop is then transferred to another loop. And that's where we raise and lower the temperature. And so all of the stuff that I'm talking about happens either directly in the sewer, in the street, or right next to the sewer, in a manhole next to the sewer. It's not happening in your facility or in your
in your building,
in your in your campus, in your university campus, in your hospital campus. It's all happening in the street, in the ground. But once that heat is removed, then you put it into your system, which then we could talk about some of the systems.
So let's do that.
There.
Let's move to that. What are the conditions? How do you decide whether you've got a Main Street, for example? And here in Willimantic, we've been talking about this. Representative Johnson has been pushing for geothermal on Main Street for many years, and is excited about the idea that we also have two fairly sizable sewer mains that run right down the center of our business district. There's a lot. It's a very dense area. We've got a lot of, I'm sure, warm sources coming into our sewer system at this point in the system. There's a lot of potential for geothermal that we see here in Willimantic. What are the conditions? When do we know we've got the right conditions to be thinking about putting in geothermal as a shared service as opposed to, and let me back up, maybe it makes sense for us to be thinking about it on a building by building basis, but the way the town has been thinking about this is some sort of downtown geothermal utility, whether that includes sewer thermal or is just groundwater based, yet to be discovered. But how do we start puzzling through whether we've got the conditions that might make that work?
Well, that's a great scenario. That's a great question. And I wish I had a quick rapid fire answer.
No, I'm trying to get free engineering advice out of you, but I know this is not an easy one.
So no, there's a particular facility in Denver, Colorado. It's the National Reserve Center. It's they use sewage thermal heat to do an entire campus. And it's been operating for a couple of years. But what they found out was, because they have this loop that goes through the entire campus. So one of the conditions is that you have to build the infrastructure. You have to have a loop, which is just a pipe underground that has water that flows through it. If you look at their facility, they're able to take heat from the sewer and dump heat into the sewer. But each of their facilities has access to this thermal loop. Now, this thermal loop, again, is not sewage. It's just the heat from the sewage has been transferred into it. And it turns out that there are some buildings that use a lot of heat, and therefore they're taking heat out. There's other buildings that spend, and this is the thing, at the exact same time, have so many humans in it, they need to run the air conditioning because the humans are producing the heat, and they want to cool it down. So they're putting heat into the system. So what they found out by working the system is that the larger their loop was, the more neutral it was, and I'm using air quotes for neutral, meaning that the amount of heat taken out is almost equal to the amount of heat put in. Therefore, they didn't have to add any. So if you have a large thermal loop with a large volume of water in it, that's called a thermal, it's like thermal inertia, if you will, but it's thermal mass. If you can be pulling energy out of it a couple hours a day, you can be putting energy into it a couple hours a day, and overall, it remains relatively neutral. And the company that runs that facility was shocked at how little energy they had to put into this large thermal system because it was self-balancing. Wow. So it's kind of you kind of have to think about that. So if you have a facility that pools a lot of energy, I'll give you another one. I wrote a report on this. It was published in 2019. I wrote it in 2016. It took 3 years to publish because the organizations kept switching. There's something called a Dam Neck Navy Base. Dam Neck Navy Base is a U.S. naval installation. It's on the beach. It is a Navy SEAL. You don't know how I'm never mind. I don't know what I'm supposed to say or not. But at any rate, they have data centers. And they were forced because the Department of Defense had a mandate that you have to change your energy use. And so they said, hey, why don't we use them? So they connected with something called the Hampton Roads Sanitary District, the Atlanta plant. So Hampton Roads Sanitary District had a large effluent conduit that went through their base out into the Atlantic Ocean. And they asked the Atlanta plant if they could have access to this thermal system. The Atlantic said yes. They worked out the details, and they built this loop. And it's initially they were kind of kicking and screaming. They felt as if the administration at that time was under George Bush was like making them do things they didn't want to do. And they said, listen, we want you to build this thing. You're going to build it and you're going to reduce energy because that's the mandate from the Department of Defense. So they did it. And after they did it, they found out how wonderful it was because ultimately all their HVAC equipment just corroded and because they're moist, corrosive air because they're on the beach, So, and all of a sudden, all of their stuff was underground, and then they had the water-to-water heat pumps, which they could put right in the basement of the buildings. Well, it turns out that their HVAC contracts were reduced. The maintenance was easier. The things worked all the time. And because the data centers that they had were producing so much heat, they kept filling up their internal loop. So they went all winter long without having to get any energy from
So
sewage.
I want to make sure I understand. They were using traditional HVAC systems, and the environment was so corrosive that they were replacing those systems a lot. They ended up switching over to a water-to-water transfer loop, and that was more stable, and they weren't finding the maintenance costs to be as high. So that's another advantage that I hadn't thought about, just the simplicity of the system. It's water flowing through a pipe and water flowing through a pipe within a pipe, I suppose, so you don't end up with lots of mechanical parts that need to be replaced.
Yes.
Interesting.
And the other is the marriage of the data centers, which had their own heat rejection devices. They had their own cooling towers.
Yep.
So they're rejecting it to the air, and then down the way, you got a barracks, which is now trying to pull heat out of the air.
So let's move from the street. Let's sort of go from if it's geothermal wells or it's a sewer thermal loop. Let's get out of the street though, and what has to be put into a building? Because I imagine. You're working with systems that aren't, electric baseboard heat anymore. You're not working with steam radiators being run by an oil burner. You've got to heat the building differently, I would imagine. Mini splits, I suppose.
Yes. Unfortunately, in engineering, the answer is always we can do that. You can get a heat pump to make steam.
Okay.
They're not very efficient, but you can do it. So if you have to have steam, you can do it with a heat pump. And again, let's just, because I as an engineer, I always wonder what's possible, what's not possible. But that's a very good question, Robert. You would want to have what we call a low temperature, or, would be a moderate temperature, hydronic system, where you would have water pumped throughout your building. So if you needed heat from it, you would take it out. And if you wanted to put heat, take heat from the building, you put it in. So you can do that. You can either make that system, again, I'm going to say it's hydronic. You have water pipes in your building. So you can make it so that you have radiant floor heating. Yep. If you redo your building, you can just have that warm floor. You can use heat exchangers, blower units, split units like you were talking about. You can have a device that, you just say, I want it warmer in here, and it just takes a fan and blows it across the coil, and warm air comes out of it, or cold air comes out of it, depends on how you program it. So that's the kind of thing. And if you really get into HVAC, you can have, there's something called cold beams or hot beams. There's all sorts of things. But you're right, it's not electric baseboard heat, and it's not a steam radiator. It is water in the system, and you can have blown air or hot water in your...
And those are common systems. We see those now all the time. Hydronics.
Yeah.
I've got hydronic heat in my home, and I haven't done many splits, but I've got a room where I want to put one in. So they are common. You can pick them up at Home Depot. This isn't high technology. This is just...
It is to me. I think this is fascinating, and I don't want to go too far afield, but I would like to ask a question, because one of the things that we've talked about, and we have this group called TENS for Connecticut, Thermal Energy for Connecticut, and Peter Millman, who's been excellent at generating more people that will support thermal energy and learning about it. And I'm hoping to have him broadcast this discussion at one of his monthly meetings. But one thing that has been raised at some of our meetings is the idea of it's a proposal in the state of Massachusetts, and that is every time they dig the road up, they put a geothermal pipe in. How does that, can you kind of connect the dots on a proposal like that?
That back to the original thing I was talking about, the Western Reserve in Denver. The larger if you start to develop a thermal energy network, which is what 10-4CT, which the group is called 10.
Yes.
10
yeah. And I got to have you sign up for it.
The thermal energy network, in a very real sense, the larger they are, the more thermal capacity you have. You're pulling and pushing all at the same time. It makes it more efficient. So the barrier to acceptance for a lot of these systems, particularly if you're going for a network, is the capital cost, is the access to the material you need to have. You need to have a pipe in the ground that transfers energy. And it's very useful to have that built into the system. It's just like the value of a sewer or the value of a water line. These are expensive investments that we make as a community, as a township. But these investments are tremendous assets that pay dividends for decades. It's expensive to put utilities into the ground, but it is always a worthwhile investment. It's just not sexy. And this is another story I was going to tell. I had the opportunity to work with some Brazilians, and we talked about the value of sewer and sewer assets, and they were like, we just can't get the politicians to invest in infrastructure because it's not sexy. You can't see a sewer. It's in the ground. You can't have a ribbon cutting, really. You can, but you really sort of can't. And it's just hard to spend that much money on something that no one appreciates. And so ultimately, it's like you don't appreciate it until you don't have it. It is it is a very good investment to make in a community. So pipes in the ground are of tremendous value. Now I feel like I'm just preaching as opposed to talking.
So I understand that the nonprofit that you're heading up is called Sewer Thermal Energy Network. You've been working, I understand, with the folks in Massachusetts to some extent. What do you know about what they're doing in terms of, at the state level, in terms of regulations or legislation or funding of programs to make this a reality?
Well, your neighbors up there in Massachusetts are trying to incentivize the development of sewage thermal energy systems. So they've put together a pilot program, and this pilot program is run through their the Department of Environmental Protection, the DEP. It's also connected to the DOE and various other branches of municipal state government. But ultimately, they've got 3 buckets of money. They will give you a bit of money to do a feasibility study. They'll give you a bit of money to do the engineering study, and then they'll give you a bit of money if you build it. Now, each of those buckets gets much bigger. And if you build a large system that's a network, you can have access to a much larger funding source. So they are incentivizing the development of this infrastructure through a pilot program by directly subsidizing the people who want to develop such systems.
Yep. And they're not alone. I mean, we're seeing this sort of energy or energy in the sense of human energy. We're seeing some excitement around this elsewhere in this region. We're seeing it in New York, aren't we? We're seeing New York get involved in sort of dealing with thermal energy networks as well. What are they doing in New York? Because I think that also might be instructive.
New York State is, again, under Governor Hochul, she came up with a blue ribbon panel. And she said, how do I reduce the carbon footprint of the New York State? And ultimately they came to the conclusion there's no way to reduce the carbon footprint if every building in the state burns fossil fuels. There's a certain baseline you can't get below. She says, well, how would you get below that? And they said, which is very much what you're talking about, the 10-4CT and the stuff you're talking about, Susan, is that you need to build thermal energy networks. And so she developed a way for the publicly regulated, the New York State PUC, to allow the publicly regulated utilities, natural gas and electric utilities, to do pilot work so that they can show that how a thermal network would be cost effective. And the reason they did the PUC was because they were allowed to be able to charge for it, so they could recover the investment they made in these projects through their existing utilities. So she's trying to establish thermal energy networks as its own utility base, as its own utility system.
Very nice. It's a very innovative approach, and I understand what the state of New York is getting at. You can't reduce your carbon footprint if you keep just getting your energy from carbon sources. If you're burning things, you're going to produce carbon, and that's going to be a problem. If, on the other hand, you can draw the energy back out of the wastewater, the waste exhaust, if you can find another way to recycle the energy that's already been produced. I mean, I've used the example in discussion here. The water that we take out of the shower, we use it at 100 and whatever it is degrees for whatever it is, for 30 nanoseconds, and it's gone. It's down the drain, and all the energy that went into it goes with it.
That's right.
Yes.
And what New York is saying is we can't get our carbon footprint down unless we make better use of the energy that we've put into that drop of water. We got to draw it back out again.
Yeah, and actually, Representative Johnson started the conversation with this. Recycling that energy, boy, that's a good idea. That is a good idea.
So that's really what Connecticut and the Connecticut State Legislature is thinking here as well, and that's what's got Windham and Willimantic's interest in this subject, because the state is beginning to think about putting money where its mouth is on this. They're starting to look at funding pilot projects, looking at design assistance, and we're starting to think, okay, if there's going to be money here from the state for us to investigate how to improve the efficiency and lower the costs of heating buildings in downtown Willimantic, we want to be, first in line.
Yeah, when you talked about that question earlier, if you have a sewer that's flowing, well, for every 1 million gallons per day, of
we're about 1.3
flow,
million gallons a day goes by the building we're sitting in right now.
Wow.
Okay, that's okay. You know what? Let me just put that into my little tickety in here. But I can tell you 1 million gallons, if you're taking 5 degrees out of it, it's 3.1 million BTUs per day, or per hour.
Wow. Wow. That's what we need to capture. Absolutely.
And that means we wouldn't have to be burning a fuel to we can replace fuel burning with that.
Right.
Well, some of that. I mean, we're not going to capture all of it.
And the other aspect of this I want to just point out is the fact that if we're able to recapture the energy we've already used and recycle it again, then the other thing is I know that we have a hard time expanding access to electricity. We have a hard time because we have no pipe coming in here. The natural gas creates the electricity as well as the nuclear power. And to expand that is a huge investment as well. So
yes.
we have a problem because in the Northeast we don't have the same resources, say you have in Pennsylvania with coal, for example, or whatever other things you use there, or where we're.
I'm laughing, Kohl. Never mind. I'm just
laugh. Go ahead, tell me. But
No. I just think it's funny because coal used to be a big business here, and it's funny because you're like, oh, that's not much coal burning,
Right.
But there was a joke. I'm working with the New York City School District, and we were joking about. Well, first of all, we're doing the feasibility to look at doing some of this work in the New York City School District, and then someone said, "Well, we don't know where some of these are," and I was like, "Any of them coal burning?" They're like, "We don't think so."
But making those transitions from one thing to the next out of all these different areas where we've had fossil fuels, and making the transition from, and I have a joke about coal and oil and all that, and that is, they saved the whales, but now it's time to save the humans.
Yeah, no, that's true. That's true. And by the way, the joke I had about the New York City public school, they don't have any coal burning. But the point is they have 1,400 schools, and so they're like, is it possible? There's probably still a furnace somewhere that could burn coal that we don't use. They're like, it's possible.
Yeah. I was just trying to point out the transitioning that we go through all the time. And we're down to our last 2 minutes.
New York City, so I just want to apologize to New York City in case I gave them.
No worries.
Maybe the impression that they're bad people.
They're on the other end of the state of Connecticut. They're not necessarily going to hear you.
Yeah. Although I hope my show goes everywhere, but nevertheless, we're down to 1 minute, Professor. Any last words?
Oh, Geez, I was not paying attention at the time. It's a lovely conversation. It's a lovely show. I think what I want to say is that sewage thermal is really is a viable form of energy recycling that we really ought to look into. And there's people like you that are going to make it a reality. So thank you.
Thank you so much for being on the show, Professor. Professor Kohl, Professor of Engineering from Drexel University in Pennsylvania. This is Susan Johnson. I'm here with our co-host today, our town manager, Rob Zarnetske. Tune in next week for another great show.
Be well, folks.
Thank you.